Welcome back to the lecture number 20. So, till last class we are discussing about the TC-SPC system, and I have already told you several parts of this TC-SPC system. Let us have a quick go through all these different component of this TC-SPC setup. So, as you remember, I need a laser source which will produce the pulsed laser light, and then this laser light will excite the sample, and the emission from the sample will be collected through this monochromator and then this PMT, and when this PMT count will come and start the stopwatch over here, then this stopwatch will also be stopped. So, you see here this is the reverse mode operation, reverse mode operation. So, ultimately the function of this constant fraction discriminator, right, you remember constant fraction discriminator, the function of this is to reduce the time jitter originates from the amplitude jitter of the photomultiplier tube. And then I also discussed about this TAC, which is time to amplitude converter. So, basically what you will going to get is the histogram of this fluorescence intensity, but it looks just in the reverse mode like a mirror image of this histogram, which is actually is, because here my start and stop are different. And you also note that I have not discussed these two things, these two work, the importance of these two polarizer over here, which I am going to discuss later. Okay. Before moving to this instrument response function, let me tell you that this count rate of this TC-SPC system is very important. Why it is important? Because in TC-SPC the first detected photon is the most important photon. It means that for a normal sample where the lifetime has some value, let us say about a nanosecond, then the photons are emitted throughout the 5 nanosecond time window. If the lifetime is 1 nanosecond, then photons are emitted throughout the 5 nanosecond time window, that we have already seen. Now, consider, and I also told you that this lifetime means the average time the molecule spent in the excited state. It means that some molecule will come back from the excited state to the ground state at the early time, some will come at a later time. So, throughout this 5 nanosecond time window, some molecule will come now, some molecule will come then, and so on and so forth. That means, some molecule will emit its photon early time, some molecule will emit its photon later time. Now, if I increase my count rate, that means the molecule, and obviously at a time I am not going to excite only single molecule, many molecules are being excited, because the number of photons in this excitation light pulse are huge. So, once I excite the sample, I must get a photon which is emitted at very later time, otherwise those photon will never be detected. That is why in TC-SPC I already have discussed briefly these things. So, in TC-SPC system the detection rate has to be very low, otherwise the probability of getting the photon which is emitted at the later time will never be the first detected photon, because in TC-SPC the first detected photon is only getting detected by the system, and you will get a count in the respective time channel. Right? If you have any question, you can ask me, right, in the portal later. Okay. So, now as I have shown you, this problem is known as pulse pileup. So, in pulse pileup, if the count rate is high, that means 0.5 photon per pulse is detected, here 0 point is over here, like so. Then the count coming up in the early time is more. That means you are not getting count at this time, this time, this time. So that means your actual decay is getting distorted. But if you decrease the count to 0.02 photons per pulse, that means so the count rate is very high, less than 2% or so. In that case, you can get the decay. In that case, the decay is the correct decay profile, which is actually showing by the molecule. Okay. Having said this, let me show you the actual measured fluorescence transient or fluorescence lifetime decay of a molecule which is called anthracene in cyclohexane. So, as you can see here, these red dots, see these red dots over here, these red dots, these are the measured intensity as a function of time. You see these red dots, these are the measured intensity as a function of time. I told you this fluorescence lifetime, the decay of the intensity with time is exponential in nature, right. But here you see it is straight line because this axis is not linear axis, this is a log axis. So, that is why it looks like a straight line, but that means in the linear axis, if this axis is linear, then it should be exponential in nature, right. So, I have all these measured data point. You see when the count is low, because this is my channel, you see here it is written as channel, that each channel, this is 200 channel, this is 300 channel, that means from here to here I have 100 channels, and each channels having some value of time, right. So, from channel 200 to 201 means some value of time, right. It could be 0.005 picosecond, it could be 0.005 nanosecond, it depends on the TAC range. I already mentioned briefly while discussing the TAC. So, depending on the TAC range, that means depending on how much time will be required to raise the voltage in the TAC from 0 to 10 volt, that you can set from outside. So, depending on that you could have different time value in each channel. So, this is the multi-channel analyzer, it works in that way only. Okay. So, if you remember when I discussed this fluorescence lifetime, I simply wrote this equation, I is equal to I0, that is initial intensity, into e to the power minus t by tau f, and I said that this tau f is the fluorescence lifetime, and I also said that it means that the average lifetime of the molecule in the excited state. So, then I also had plotted these things, I versus t, and I told you that if this is the time of excitation 0 and excitation is usually very fast in time, that means no time will take for the excitation, and if the excitation pulse width is a delta function, then immediately at time t equal to 0 you will going to create some population which will decay exponentially. That means this decay will be something like this, exponential decay. Okay, let me draw a line like this, exponential decay. This same thing if I now plot on the log scale, then this will looks like this. That means at time 0 there is no count and the count is very high at time t equal to 0. So, everything starts from here, from this point, then it decay. This is in the log scale. So, it is just started from here at a high value and then it is decaying. But in this case you see the red dots as I showed here, these there are some red dots are still even here. It looks like that something is rising and then it is decaying. It looks like something is rising from here to here, something is rising and then it is decaying, right. But from our basic equation like this, I do not see any rise, because it is simply decay, exponential decay. So, the question is, from where that rise part come? The answer is very simple. To get this equation, or while explaining this equation, I said two words. That word is that excitation is very fast, and that is true. Absorption is in the order of 10 to the power minus 15 second, that we have already seen. Another thing what I said is the excitation pulse is a delta pulse. That is not correct. That is not correct, because I do not have such kind of delta pulse excitation light source. What I have the pulse laser output. So, that those pulse laser has some specific pulse width. It could be 1 nanosecond, it could be 100 picosecond, it could be 100 femtosecond, but it is not 0. Because of this, I will not going to get just simply all the population at time t equal to 0 is maximum. So, if the pulse width is something, it could be 1 nanosecond, it could be 1 picosecond, then when the tail part of the pulse will interact with the sample, then few molecule will go to the excited state. But when the peak of the pulse will interact with the sample, then most of the molecule will go to the excited state, and when the later part of the pulse will interact with the sample, then again few more molecule will go to the excited state. That is why in this case decay is distorted. And to analyze this, right, you see these red dots, it is like this shape. So, to analyze this, that analyzed curve is this green curve, as you can see here. See this green curve, this is my analyzed curve. To get the value, this is the fitting line, right. Then I will understand what is the value of tau A from here. So, to get this, I also need this blue one, as I have mentioned over here. I also need this blue one, that is called the IRF or lamp, that is the instrument response function. It is a collective response of the laser. How many device we have in TCSPC? Laser, I have constant fraction discriminator. What is the job? It is reducing the time jitter coming from the amplitude jitter of the PMT. Then I have the PMT itself, where it has some transit time spread, which I cannot really, I can reduce it, but it cannot be 0. So, taking all these time error component in the TCSPC setup, I will going to get a collective response of the instrument, which is called the instrument's response function. And let me show you that this instrument response function, what I have written here, is response of the instrument to the 0 lifetime sample, right. You note here it is written 0 lifetime sample. What is 0 lifetime sample? 0 lifetime sample is nothing but the scattering. Scattering is it 0 lifetime, right. Once there is a light, there is a scattering. If light is stopped, scattering is stopped. So, instead of taking some fluorophore, that some molecules which emits light, if I now can take a scatterer, that means that scatterer will going to give me scattered light. That could be Rayleigh scattering, that also could be Raman scattering, does not matter, because in both the case this scattering is instantaneous process. Okay. Now, so I will going to use a scatterer. So, some people use the dilute milk, that is also very good scatterer. So, dilute milk one can use a colloidal silica. So, whatever scatterer you want to use, you can use. So, those are thus that scattered light is a 0 lifetime sample in our case. So, in this case, so I will get the response of the instrument, is not it. So, if the response of the instrument is only depends on the pulse width of the excitation laser source, then if I change the laser source, then the IRF of the system will change accordingly. So that we can check how this collective response actually change by changing the different component of this TCSPC system. So as I told you that this instrument response function depends on the light source, depends on the detector, depends on the electronics part. Here this is my CFT, here is my PMT, here is my PMT, here is my CFT, and here is my laser. Okay. So that can be written like such kind of form, where this is delta TE is my excitation FWHM, this is the laser part, and this I, this is the instrument part. So one can calculate easily that if the detector response transit time spread or response time is 25 picosecond, electronics part is 50 picosecond, and laser is 10 picosecond, okay, then the total IRF will be something like 56 picosecond. That obviously we have to measure. We have to measure how? By changing the sample with a scatterer, and just simply change the wavelength of the emission monochromator as same wavelength of that of my laser light, then I can simply monitor it. If you want to monitor the Raman scattering, then you can also go to the different wavelength than the excitation light and measure the instrument response function. Now what I have done, I have just changed the laser from 10 picosecond to 0.1 picosecond, that means 100 femtosecond. Is much better laser, but if you calculate it, what you are going to see, the IRF remain 56 picosecond. That means it has some effect, but it is that effect is not so prominent here, because it is overruled by these two value. So if you change the laser from 10 picosecond to 100 picosecond, then you see the effect over here. Now the IRF will be 115 picosecond. So the limit is over here, the electronics part, in this case the electronics part, in this case the laser part, because it is the highest value among these three. So IRF is like the highest value. In this case the highest value among these three is this one. So the IRF is guided by this value, that highest value. In these three, in this case the highest value is this one. So IRF is like this 56 picosecond. But the problem is that you cannot go below 25 picosecond. So IRF cannot be less than 25 picosecond in case of TCSPC system. Okay, whatever I said, let me also show you in this animation. So for the delta pulse excitation, immediately at time t equal to 0, I got maximum intensity, and this is simply decaying like this way, right. So the intensity as a function of time can be written as IT equal to alpha. So that initial intensity exponential minus t by tau. But then I said that this cannot be delta, it has some pulse width, right. So let me take this LT as the lamp intensity as a function of time, which is denoted by this part, and I have taken this mid part as my time 0, right. So when this part, the negative time, is interacted with the sample, then some molecule will go to the excited state, and immediately after going to the excited state, those molecule will start decaying. So if when this part of this excitation pulse will interact with the system, those molecule, like some other molecule will go to the excited state, and those molecule immediately after excitation will start decaying, and so on and so forth. That what I am trying to show you over here. So this part is showing a fluorescence decay like this at time delta minus 4. This part fluorescence decay is like this. Please note that this is in the log scale, here is not linear scale. So in this case, so here all these decays are straight line, and here there is a decay. That means the total fluorescence decay will be this plus this plus this plus this plus this all these things, and it will looks like this black curve. So, there is something rising and then there is something decay. But as you know, if I have a delta pulse, then it should be a simple like this, and then I can fit it and I will get the value of tau. But from here you cannot fit this with such kind of equation. This cannot be fitted with such kind of equation, impossible. So, I have to do something to get this value of tau. What I should do? That is my question now, and we are going to discuss that. Okay. Let me take this as my excitation pulse at time t equal to 0. In this case, the lifetime is I t equal to e to the power minus t by tau. If I take this as 1, so this 1 is over here, 1 into e to the power minus t by tau. Now, let me take the broad pulse, this is my delta pulse. Okay. Now, for this broad pulse, I can think of that this broad pulse, here is my T0. This broad pulse is consist of 3 delta pulses at per my choice. I decided to think like that. This is my first one, the second one is in the middle, and this is my third one. So, this is actually coming at time t1, this is at time t2, this is at time t3. So, each of these pulse independently I can think of is giving the fluorescence emission, and obviously each of these will have its own fluorescence decay. So, the first one will looks like this, the second one will be like this, because second one is the higher intensity. So, the intensity will be high, and the third one will be like this. So, altogether what I will have is like this. So, everything will add together. So, now the decay looks like this. It is no longer a straight line starting from an initial value, which was here, starting from initial value a straight line. It is now distorted. Okay. Let me write the individual equations here. For the first one, I can write I1t equal to the intensity LT1, because it has some intensity and the some intensity over here, and the fluorescence intensity at time t equal to 0, t equal to T1 will be proportional to that intensity. So, I simply write LT1 e to the power minus t plus T1 divided by tau. You got my point? Here in this case, it is not simply minus t by tau, because some time T1 is already delayed over here. This is not starting from T0. So, minus t plus T1 divided by tau. For the second one, I2t is equal to L T2, because the intensity is little higher over here, and the fluorescence intensity will be proportional to the excitation light intensity, that we all know, e to the power minus t plus T2, that means this is at some other time, divided by tau. For I3t, similarly I will write T3 e to the power minus t plus T3 tau. So, the total fluorescence intensity I can write NT equal to I1t plus I2t plus I3t. So, I can simply write L T1 e to the power minus T minus T1 by tau plus L T2 e to the power minus T minus T2 by tau. I just took the negative signs out over here, plus L T3 e to the power minus T minus T3 by tau. Good. So, this I can write as L T1 I T minus T1. Look here, some constant e to the power minus T by tau is this T. So, if I have T minus something, then here also T minus that time. So, L T1 I T minus T1 plus L T2 I T minus T2 plus L T3 I T minus T3. This I can write as a sum over I, or let us write Tk is equal to 1 to 3 L Tk I T minus Tk. So, this is for the summation for this 3 pulse. Here is my number 1, number 2 and number 3. Now, I can consider that I have infinite number of delta pulse which is making this excitation pulse like, I can say so. So, what I can write, for many delta pulses, this n Tk can be represented as sum over Tk 1 to Tk L Tk to I T minus Tk. For many things I can simply integrate, integration 0 to Tk L Tk I T minus Tk dTk, right. So, this is the effect. So, this is the effect of many delta pulse in that excitation pulse light. Okay. Now, this LTK is my lamp profile. That means, this is nothing but that what I said, here is my one delta pulse, here is my another delta pulse, another like that, right. This is T0, T1, T2 and so on, that is what I said. So, this is nothing but instrument response function, that is the response of the instrument towards the 0 lifetime sample. So, this is IRF, I can measure it. So, this is measurable quantity. This NTK, this is nothing but your measured fluorescence decay. So, now if you have this LTK looks something like this, just I am drawing it. Let us say this is your LTK that you have measured, and you have just guessed some guessing that the fluorescence lifetime of this sample is 4.2 nanosecond. So, for this 4.2 nanosecond, simply this will follow the e to the power minus t by 4.2 nanosecond. So, the intensity will decay accordingly. So, ideal value, ideal case. So, simply you will get such kind of curve. So, this is your true IT which has the form e to the power minus t by tau. So, this guy and this guy will give you from this equation, this is nothing but this I, the form of I, this LT is nothing but this. So, these two will give you like such kind of decay. This is your calculated decay. What is your measured is over here. This is the calculated. This is your measured. This is gauge value. So, the measured one and this calculated one, let us say the measured is looks like this, the measured one is like this. So, then after you calculate, you compare with the measured one. If they are same, no, they are not same. So, you change the value, gauge value to a different value. Then again you merge with this according to this equation. So, then the different you will come like this way, still it is different. So, you again change and once and sometime and for one value of this tau, this will be similar to the measured value, that is called the least square fitting method, and you will get the lifetime of your sample. So, like this way we are going to measure the lifetime in TCS/PC system, and this process is called the iterative reconvolution technique. Okay, with this let me stop here and we will continue our discussion in the next class. Thank you very much.